Welcome to this explainer. Let's just jump right in, because today we are diving into a truly fascinating analysis. It sets out to prove something pretty radical, that failure isn't just an accident or a stroke of bad luck. It is actually a universal mathematical property of systems. Whether we're talking about human psychology, complex computer algorithms, or those sprawling societal institutions we all deal with, systems inevitably break down. But what if those breakdowns are entirely predictable? What if they're governed by strict, unforgiving mathematical laws that dictate exactly when and how things are going to fall apart? Well, that is exactly what the massive document we're exploring today sets out to prove. It uses rigid mathematical proofs to explain literally everything from why your computer crashes under a heavy load all the way to why modern societies become so irreconcilably polarized. It's a completely fresh, mind-bending way to look at the world around us. But before we get bogged down in the heavy math, the author actually anchors us with this really profound insight from the poet Charles Bukowski. The quote reads, "What matters most is how well you walk through the fire." And I love this because it establishes a very hard culture baseline right up front. It reminds us that experiencing failure, that metaphorical fire, is just a universal baseline for any system. At the end of the day, what counts isn't your pristine pedigree before the trial begins, or how perfectly your system was designed on paper in some sterile laboratory. What matters is process over pedigree. It's all about how the mechanisms actually handle the immense stress of the fire once they're actively burning inside it. It's a really powerful, humanizing starting point before we transition into the cold, strict logic of systems. And we really are dealing with a massive, ambitious scope here. This document explores the anatomy of failure across multiple disciplines. But the absolutely crucial thing to understand is how it's written. It's coded in a formal proof language called Lean. We are talking about 40 incredibly dense files, intricately linking art history, mechanism design, modern algorithms, and thermodynamic principles into one cohesive theory of failure. Now, if you're not familiar, Lean is a theorem prover used by advanced mathematicians. That means the author isn't just speaking philosophically about failure here. They aren't just tossing around fun metaphors. They are literally attempting to mathematically prove failure as a fundamental law of nature, mapping out the precise geometry of why things inevitably fall apart.
So, here is our roadmap for unpacking all of this. First, we'll cover the anatomy of failure. Second, the mathematics of breakdowns. Third, the truthful cap theorem. Fourth, modern systemic deficits. And finally, excavating the void.
All right, let's start with part 1, the anatomy of failure, and our cultural anchor. Before we can calculate the hard math, we really need to understand how human culture and psychology initially process a breakdown. To vividly define a system in crisis, the author turns to art history. Specifically, they look at Francis Bacon's famous, haunting paintings of the Screaming Pope. In the text, the author notes that Bacon actually wanted to paint the scream more than the horror. And this is such a brilliant way to illustrate the kinetic agony of a biological machine in full-blown crisis. It prioritizes the felt vibration of panic. Think about your own nervous system discharging when you are under immense stress. Bacon isn't just painting a scary picture for the sake of it. He is capturing a biological system hitting its ultimate breaking point and venting that catastrophic pressure. It is the raw, visceral reality of a failing mechanism. Moving from biology into the realm of psychology, the document then draws on Carl Jung's work, specifically his 1951 book Aeon, to unpack another catastrophic mode of failure. It argues that failing to integrate the psychological shadow creates a massive security risk. Think of it like a huge corporation hiding a critical internal vulnerability just to keep its stock price artificially high. When a system, whether that's a single human mind or a sprawling organization, suppresses its darker, unintegrated parts, those hidden forces don't just magically disappear, right? They silently and effectively steer the system toward total collapse. The true danger isn't the monster you can see approaching on the horizon. It's the monster you suppress internally that eventually crashes the entire system from the inside out.
Okay, moving to part 2, the mathematics of breakdowns, the engine of entropy. Now that we've established the emotional reality of failure, let's dive into the hard math where this lean code really goes to work. The theory defines a fascinating concept called cost algebra entropy. It stems from the no-cloning theorem, which states that whenever a system attempts to perfectly clone a state, it inevitably generates a gap. Let's put this in plain English, all right? Whenever a system tries to perfectly copy itself or perfectly transfer its data, it requires energy. And in that transfer, a tiny bit of fidelity is always lost. The mechanism fundamentally fails to perfectly preserve the original score. That tiny loss of fidelity, that is the entropy generated by the clone. It is essentially the categorical version of the second law of thermodynamics translated directly into system logic. Every single copy, every replication, introduces an unavoidable, measurable decay.
So the absolutely crucial point here is what happens when that entropy continually accumulates. Eventually, we hit what the author calls the Landauer deficit. You can think of this exactly like a computer processor overheating. When a system asks for more energy than the hard physics of the machine can actually handle, it hits a thermodynamic ceiling. And once you cross that line, the request isn't just gracefully delayed, it is flatly rejected and a deficit is officially recorded. This Landauer deficit quantifies exactly how far past the safety limit a system has been pushed, which triggers a mandatory remediation process. The system literally cannot move forward until it cools down and pays off that specific mathematical deficit.
Now, to manage this completely unavoidable deficit, the system relies on a mathematical failure controller. This controller faces a strict optimization problem and must choose one of three actions to survive. First, it can keep multiplicity. This means it ignores the heat, tries to maintain its current complexity, and just brutally pushes through the pain. Second, it can pay vent, where it actively sheds the load, dropping tasks and paying a cost to vent the built-up pressure. Or third, it can pay repair, where it takes on massive structural repair debt, shutting down core functions to completely fix its broken foundation. The math strictly dictates which path minimizes the overall score penalty based on how badly the system has already decayed.
Which brings us to part 3, the truthful cap theorem. Let's look at the absolute impossibility of perfect mechanism design. You see, there is a hard mathematical ceiling in complex systems, and it's represented by the number 3. In mechanism design, there's a well-known concept called Arrow's impossibility theorem. It dictates that there is an absolute maximum number of desirable properties you might want in a complex decision-making system, which is typically 3. But mathematically, you can only ever achieve 2 of them at any given time. It's a fundamental law of limitations. One desirable property must always, inevitably, be sacrificed to maintain the other 2. There is no way around it.
The author introduces the brilliantly named truthful cap theorem to illustrate this exact sacrifice in action. It mathematically proves you cannot simultaneously have a perfectly truthful system and a perfectly budget-balanced system. Here is why this happens. If you want a truthful system where actors are forced to actually internalize the external damage they cause, you have to financially incentivize them to reveal their hidden costs. But paying those incentives completely blows your budget. On the flip side, if you strictly enforce a balanced budget, actors will naturally hide their externalities to save money, meaning they will constantly lie and game the system. You mathematically cannot have both total truthfulness and a perfectly balanced budget. Something has to give.
All right, part 4, modern systemic deficits, or what the author calls the modern archon. Let's apply these exact mathematical limits to the institutions and technologies we interact with every single day. The source neutrally maps this abstract math right onto very real-world issues, defining them as modern systemic deficits. Take social media algorithms, for instance. Mathematically, they operate as an interversion refusal whipsaw, meaning they are structurally designed to maximize friction. They whip you back and forth between anger and validation rather than ever allowing a stable consensus. AI hallucinations, those are defined as the counterfeit spirit, generating noisy, confident copies that completely lack underlying structural density. Institutional rot is simply universal amnesia, where an organization mathematically forgets its highest density foundational purpose and just reverts to bureaucratic noise. And extreme polarization, it maps perfectly as the binary debt.
And if we look directly at the raw lean code from the document, extreme polarization isn't just viewed as an emotional or political failing. It's defined completely neutrally as a state of infinite systemic debt. The code maps a state where 2 agents exist at -1 and +1. Now, if you add those together, they mathematically cancel out to 0. On the surface, the system looks completely balanced and at peace. But fundamentally, those agents fail to resolve. They are pulling in opposite directions with absolute maximum force, leaving a massive, invisible tension that is ripping the underlying system manifold apart. It's an impartial, incredibly brilliant structural view of why societies stay locked in permanent conflict while pretending everything is completely fine.
Now, you might be wondering, why should we trust that these mappings are accurate? Well, to ensure these observations are structurally sound, the analysis relies on a strict methodological ladder. Because in a world completely full of noisy data, a single measurement means almost nothing. Evidence has to climb the ladder, from a single measurement to replication using the same methodology to replication using different methodologies, until it reaches the absolute gold standard, cross-witness triangulated durability. This means 3 or more entirely independent models have reproduced the exact same failure.
Only when it hits that triangulated peak is a failure considered a fundamental structural truth rather than just some temporary fluke in the system.
Finally, we reach part 5, excavating the void, charting the completely unknowable. So what actually happens when a system breaks down so profoundly that its boundaries sit behind an unknowable thermodynamic barrier? The text introduces a brilliant epistemological process called void archaeology. Think of it kind of like trying to map a black hole. You mathematically cannot see inside it, but you can study its edges. First, you project. You cast light as far as you can to witness the claim at a measurable depth. Second, you scrape the void. You deliberately probe that event horizon to find exactly where the light disappears, exhibiting a negative witness. Third, you reconstruct. By connecting the dots of where the light failed, you draw the exact boundary of the blocked claim, mapping the shape of the wall even if you can't see behind it. Finally, you classify the epistemic state of the system based on the shape of that darkness. It is an incredibly powerful way to map the exact shape of the unknown.
Which brings us to our final takeaway. We now know that failure isn't an accident. It is a guaranteed structural budget that you must eventually pay, dictated by the heavy laws of entropy, the strict limits of the Landauer deficit, and the impossibility of perfect mechanism designs. Since the math proves that the bill always inevitably comes due, the ultimate question is this: if systemic failure and entropy are mathematically unavoidable, are you actively designing your systems to collapse gracefully, or will you blindly let them burn uncontrollably? How will you map the voids in your own systems? Thank you so much for joining me for this explainer, and I truly hope it changes the way you look at the breakdowns in the world around you.